Hello, today we're gonna work on the Canadian Computer Computation Test year 2018 senior problems, problem S3, RoboThieves. So this is basically that there is a n by m grid and composed of cells. And a robot is in one cell and it needs to escape, and the cells is either empty or a wall or a camera or a conveyor or the robot's initial position. So basically, if there are conveyors that the robot can get on, and the conveyors can move in one direction to the cell that it cannot move further, and for the cells with a C, that means it's a camera. So all the empty cells along the way, either up, down, or left, right, that are controlled by the camera, and but conveyors can pass the camera. If the robot is seen by a camera, then it's caught. And then, so for each empty cell, it's possible an exit. So what we need to calculate is from the robot's initial position to each empty cell, how many steps it needs. And then the input specification. So the first line, there are two integers for the n and m. That's for the size of the grid. Then you will get the cell information for each row in the grid. And from the input, we need to know where the robot's initial position is, and we need to track all the empty cells. Then we need to calculate the steps that are needed from the initial position to the current to each empty cell. And then in the output specification, it's not it's very simple. So each line there is an integer indicates the steps needed from the initial position to an empty cell. So and the order of these empty cells is in row major order and then column. And then we have samples here. So this is the first one. We can see this is a 4x5 grid, and we have 5 columns, 4 rows, and we have W as the border, which means the wall, and then we have empty cells at row 2 column 2 and row 2 column 4 and row 3 column 4, and the initial position at the row 3 column 3. So here, let's say the first empty cell is this one, row 2 column 2, but as you can see, there are walls surrounding this cell, so there's no way to move from the initial position to this empty cell. So you can say -1, that's in the output. And for the empty cell at row 2 column 4, you can say from the initial position 2 steps are needed, so we have 2 here. And for the empty cell at row 3 column 4, it's only 1 step needed, and we have this one here. So and we have sample 2. This is a 5x7 matrix. So you can see the initial position is here, and the first empty cell is here, and you can take 1 step up, as this is a conveyor. You can move up to here. There is no more steps needed. It's still 1 step, and then you get here, and then you step left. This is another step, so you have 2 steps now, and this conveyor take you to this empty cell. So to this empty cell, it's 2 steps needed, and to this one it's 1 step needed. And to this one, when you get here, it's 2 steps. You step left further, and then take the downward conveyor, and you can get here, and that is 3 steps. That's why we have 2, 1, 3. And then for this one, as even though there is a camera here, but this is an upward conveyor, so the camera cannot see the robot in the conveyor, so it's okay. But the camera can see past the conveyor, so this one is under the control of the camera. So that's why this one is not reachable. So you have -1 here. And then for this one is controlled by the camera, so you cannot move there. And for this one, it's 1 step. We have the last one. Okay, so this is the problem. We need to analyze how in our code we should calculate the steps. Of course, you can have a function to do the calculation from the initial cell to every empty cell. But that's a lot of duplicated calculation. Let's say if you want to calculate the steps from the initial position to this cell, you need to calculate this cell and this cell. But next time you calculate the steps for this cell, you need to calculate this cell and this cell again. So we don't do it that way. We can do it. We can start from the initial position and then just move to all the ways. If we can move further, we just move it, and along the way we track the steps to each empty cell. Here we can use a tree structure, and we can take the initial position as the root of the tree. So we can use a tree structure for this analysis. We use the initial position as the root of the tree. Then we need to find the subtrees. We have the up cell, so there is 1 subtree, it's a W. We have the down cell, it's another subtree, it's W. We have the left, so we have the initial one is in the tree, and the up cell, the down cell, and now the left cell is a W, and the right cell is an empty cell, and this one, and also this one. And now as W is the end of the subtree, so it's only this empty cell that we need to care to check the subtrees for this node. So for this dot, we have the up cell, it's another dot, and then we have the down cell, it's a W. And then the left cell, as it's the initial position, it's already in the tree, so we don't care about it. And now the right one, it's another W. And then this one is the one we need to consider more. It has the up cell, W, and then the down cell is already in the tree, the left is already in the tree, and only the right one. And now we get to dead end. There is no more nodes that we need to consider. Or the left one, like this one, is not reachable, so it's -1. There is no way for the robot to get there from the start position. So here we know to get to this empty cell, it needs 1 step, and to get to this empty cell, it needs 2 steps. It's about at which level your node is in the tree. So we can say this in this way it's easier to we can say in this way it's easier to calculate the steps. Okay, now let's see how we do it in code.